Hello, everyone, and thank you for coming back. So, as you hopefully know by now, we have a midterm scheduled for next Tuesday. That midterm will consist of 10 multiple choice questions and two long answer problems. And you will have the materials available between 3 p.m. and 7 p.m. through my courses. So, today we're going to start to talk about some material that's not on this exam. So everything that will be covered on this exam has already been covered in lectures for the class. So you can revisit those lectures either in the live versions or the pre-recorded versions through the My Courses webpage. Does anyone have questions about the exam? All right, then we will get started. So up until now, right, so your whole first midterm will be talking about closed systems, right? So we know in a closed system, we're separating the universe into the system and the surroundings, and no mass can transport across the border between the system and the surroundings, but we can transfer heat. So what we know is that the change in energy in the system is equal to the heat transfer minus the work. And this is great as long as mass is not coming into or out of the system. The problem is, what we've learned so far in the class is that mass itself carries some energy with it, right? This internal energy we've been talking about goes along with the mass. So if we have mass coming in and out of the system, we're going to have to sort of use a more complicated version of the first law that tries to account for the energy that's coming into the system or leaving the system with the mass. Right? So we know for closed systems, right? So, if you're thinking about studying for your exam, this is what we know about closed systems that, okay, when we say, is the system open or closed? When we answer that question, if it's closed, we know we have this version of the first law. Then we know that if we make some assumptions about the relative importance of different energy terms on the left-hand side, we can get that it's the change in the internal energy that's equal to Q minus W. We know how to find work. That's the integral of PdV. And then we can find delta U by taking the mass times the change in the specific internal energy. To do that, we need to ask ourselves, what's the fluid? And if it's water, I need to figure out which phase I have, whether that's a liquid, a vapor, or some mixture of the two, or whether the fluid inside my system is an ideal gas. And if it's an ideal gas, I can use the ideal gas law, but I also have to worry about what's going on with the specific heats. Is it constant specific heat, where I can say delta U is CV times delta T? Or is it a variable specific heat, when if I'm dealing with air, I have to look at table A22. So that's what happens if the answer to is it open or closed is closed, right? So we sort of know how to do that now. So we're going to start. So the next part of the class, the next sort of section of the class, deals with open systems for the most part. But then we do start to get into what happens when we put several processes kind of in a row and chain them together to make a cycle. But on the path to that, to trying to understand how a nuclear power plant works, that's the first type of cycle that we'll look at. We have to first ask ourselves, what happens to the mass? So I know in an open system that the mass is going to come into the system and or leave the system, but I have to have a way to track how much mass is coming in and how much mass is going out, because I know that the mass itself carries some energy with it, depending on properties like the temperature or the pressure of that mass. So when we look at open systems, we'll talk a lot about control volumes. So the control volume is either the real or imaginary boundary that separates my system from my surroundings. So like I said, like it says here, this can be kind of an imaginary boundary, like it's shown in here, this kind of dotted rectangular prism, right? If I got my geometry correct. And then, or it could be a real physical boundary, at least for the most part, if we were talking about flow through a pipe, maybe our control volume, part of the control volume is touching the inner wall of that pipe, right? So the whole volume here is called the control volume, but the actual like surfaces of this volume we call the control surface. That's actually the boundary, right? So that's the border between the system and the surroundings. That's our control surface. So when we start to do these open systems, there's a couple questions that we need to be able to answer. So the first is going to be, where do I draw my control volume? Right now, the control volume might change over time, at least theoretically it can, right? But we need to know where we're going to draw it. So again, this is kind of my attempt at drawing a pipe, right? So what I typically try to do is have some surfaces on this control volume touching basically impermeable boundaries, right? So the pipe, the inner wall of this pipe is impermeable. Mass can't go through it, right? So here, part of this surface is right touching that impermeable surface. But then there's also going to be some parts of your control surface that are permeable, because otherwise, how can mass get in and out if there's not parts of your control surface that mass can pass through? So if you're talking about a pipe, typically I would draw my control volume so that part of these surfaces are perpendicular to the flow, right? So that the flow is going right across this boundary at 90 degrees. So we need to know where to draw our control volume. We need to know what happens to the mass. So we have to have some accounting for how much mass is coming in and how much mass is going out, because only then can we then start to account for the energy. Some of that energy is going to be heat and work, like we've been talking about, but some of the energy change in our system is just going to be from this mass going in and out. First, we're going to talk about how we deal with accounting for the mass that's coming in and out. And then after a couple classes, we'll talk about how do we, what does the first law look like for these open systems? So the equation that's going to govern a lot of this is conservation of mass, right? So this is basically saying that mass cannot be created or destroyed, right? But if we think about my system, right, so I have here a cup. I know you can't really see me here, but I'm holding a cup that's full of water, right? So my system is the cup, right? So maybe my control volume is the cup, but I have some mass of water that's in my cup, right? If I drink from that cup, then the mass goes down, right? So in order to find here the change in mass in the system over time, right, the mass in the system at time 2 minus the mass in the system at time 1, I have to add up all the mass that came in and subtract all the mass that came out, right? So this cup, I can drink out of it, but it's not raining in Rochester today, but that happens a lot. I could put my cup outside in the rain, and there would be some mass that's coming into my cup through that top part of my control surface, right? The open part of my cup. So here we have the change in the mass stored. This looks a little bit like our conservation of energy for closed systems, right? Where we had the change in energy on the left side, but here it's the change in mass, M2 minus M1. We got to add up all the mass that comes in and subtract all the mass that goes out. So this is the sort of time-elapsed version of conservation of mass, right? And in the words here, it talks about the net inflow of mass, which is just the sum of all the masses in minus the sum of all the masses out, right? So, maybe this is because every field has this, but sometimes we have these funny words for things. You got to sort of break out your engineering decoder ring. So sometimes people will call this conservation of mass equation, sometimes they refer to it as continuity, right? So if someone says, oh, we'll use the continuity equation, what they mean is conservation of mass. So here's this sort of branching pipe system that's an open system, right? I'm going to draw a control volume in this system. That's this dashed line. And again, so I'm touching the walls where I can, and then I'm drawing lines that are perpendicular to the surface when I can't sort of go along the surface, right? So I have some amount of mass in my system at time 0. So that's the initial mass of my system, right? So I would know M1. Let's say I blocked all the outlets and I added mass to the system, right? This happens, when you flush your toilet, I don't know if you've ever looked inside, but there's a little flapper. It comes down, so it shuts the exits to the reservoir, and then water gets pumped in, right? And the system starts to fill up. So in this case, we would be taking away all the places where mass can go out. We're adding mass into the system. So in that case, we know that M2 would go up, right? And this probably seems a little bit trivial in this elapsed time format. We could do the same thing where if we stop the inlet, again, if you think about this reservoir from the toilet, once the flow stops coming in, if you flush the toilet and the flapper opens, now you allow mass to go out and the water drains from the reservoir, right? So as we increase mass out, then the mass goes down. So this hopefully kind of shows you a little bit. It's a little bit trivial maybe, but it kind of shows you that the form of this equation makes sense as long as we're talking about mass, these changes in mass, always in absolute terms, right? Then our signs are correct, right? So then we can find the mass at the outlet. So this is our continuity equation if we're talking about elapsed time, right? So the change in the system mass is determined by the mass in and the mass out. Now, I'm sure that this is no big surprise to anyone, right? There's another really sort of special case that we can talk about, right? So let's say that it's a rainy Rochester day and I take my tea mug and I put it outside, right? So there's water that's raining into my cup now. So it would normally fill up, right? But I could also have a case where I have a little bit of a hole in my tea mug and that there's water leaking out at the same time. Now, if the water that's leaking out leaks out at the same rate that the water enters, then the water level in my cup stays the same, even though there's water coming in and there's water going out at the same time. We can get to this special state, which we call steady state. And at steady state, nothing changes, right? So that means that the amount of water coming in doesn't change, even though you can still be having water coming in, but the rate at which it's coming in doesn't change. The rate at which it's going out doesn't change. And in the special case, when those two rates are equal, when the amount of mass coming in is equal to the mass going out, so that the water level remains the same, then the amount of mass in my system is not changing with time. So then we have this special condition that we call steady state. So a lot of different machines will operate at steady state eventually, right? Like a lot of times, maybe you'll think about, you start your car in the wintertime, right? Again, if you're in Rochester, this is a common occurrence, right? Not now, but it's a common occurrence. And it's cold when you first get in there, right? So you turn on the heater in your car, and then eventually you get to some temperature, and you turn it on, you're warming the car up, right? It takes some time for the temperature in the car to get to some level. But if you don't change it, eventually it will get to some constant temperature where the heat transfer into the cabin from your heating system and the heat transfer out of the cabin from the fact that it's cold outside will be equal, and your temperature will stay the same. So you get to this steady state. And that happens with a lot of different systems, maybe not when you turn it on, but after some amount of time, if you run it at constant parameters, then you'll get to a point where the system is at steady state. So at steady state, the change in the mass of the system is 0, which means that all the mass in, the sum of all the masses in, is equal to the sum of all the masses out. So that's kind of the elapsed time format version of this equation. But you'll see that when we talk about these open systems, we don't usually talk about them in terms of elapsed time, which is what we did in closed systems. Usually we were seeing how a system would perform over time, where our subscripts were denoting different points in time. But what's usually going to happen in these open systems is we'll have to deal with the rate of change, and our subscripts won't be pointing to points in time anymore. They'll be pointing to like physical locations at a particular instant. So if we were interested in how things are changing, right? Now, you might, your spidey sense might be tingling here because the math of change is calculus, right? It's interesting. One of my neighbors is a physics teacher in high school, and we were talking the other day, and I was saying how, kind of lamenting as my kids are sort of watching some TV, and they talk about how, like, they're told how hard calculus is, right? And I thought when I was in high school that the math they taught us about, like completing the square, which is another way to find maximum and minimum values, was like way harder algebraically than learning calculus. So hopefully you feel that way too. I kind of make some jokes about trying to minimize the amount of calculus that we do, but hopefully you start to feel comfortable with it, right? So if we start to look at how things change with respect to time, then we start to look at calculus, right? So we would divide all the terms in this equation by some delta t. And then we would say, well, what happens if that limit of delta t goes to 0, right? Or we start to talk about some infinitesimally small bit of time, right? So now we're not looking at it's like we're looking at the rate of change of these different terms in our equation, right? Or at least the left-hand term becomes a rate of change. We denote these things a little bit differently, right? So you might be aware of this convention that we have that, if you have d something by dt, that's the same as something dot, right? Now in this class, we don't quite use those things interchangeably. So in this class, if I talk about dm by dt, this is the rate of change of mass in my cup. So this is related to, when my cup is sitting out there in the rain, it's related to how is the level of my cup changing, right? Now that's just height, but I mean, you can turn height into volume and volume into mass, right? If you knew the density. So this, when we have something that's d something by dt, that's actually the rate of how something's changing with time. Now here, when I talk about m dot, this is a mass flow rate. So it still is mass divided by change in time, right? But this, when we talk about something dot, this is like, again, if I'm talking about that that cup that's sitting out in the rain, m dot in is the rate at which mass is entering my system, right? So if I took all the mass that came in through the lid, right, and divided that by the amount of time that I measured it over, then this would be the rate that was going in. But that doesn't mean it can be constant, right? So it is a rate, but it doesn't necessarily change with time, this m dot in term and the m dot out term, right? So again, if we look at this, like the verbal definition of this equation, dm by dt, this is the rate of change in the amount of mass that's stored within the system. M dot in, this is the sum of all the mass flow rates, this is the sum of all the mass flow rates into the system. M dot out is also the sum of all the mass flow rates out of the system. And the reason these are sums, right? So again, if we thought about this branching pipe network, I could have more than one inlet into the system and more than one outlet out of the system, right? So this is the net inflow across the boundary is still the sum of m dot in minus the sum of m dot out. So again, I can draw this kind of branching pipe system. And now inside my control volume, I think about dm by dt, the rate at which mass is changing inside my system. To get that, I would add up all the mass flow rates into the system and all the mass flow rates out of the system. So the change in the system mass is determined by the mass flow rate in and the mass flow rate out, right? And again, in this class, most of the time, we're going to deal with this very special case, which is steady state. So again, if my cup is out there in the rain, this is the case where the leak is coming out at the same rate that the rain is driving water into my cup, right? So in this steady state case, the rate at which mass is changing in my cup is equal to 0, because at steady state, the rate of change of everything in my system is 0. So that means that the rate of change of mass in my system has to be 0, right? But these other m dot terms, which are not really rates of change, even though they're rates of how much mass is coming in, right? They're not necessarily changing with time. So here, this is the mass flow rate in minus the mass flow rate out. So in this special case of steady state, which is a condition that we like and that we'll talk about most of the time in this case, m dot in is equal to m dot out. And it makes sense to talk about this, if you're talking about a nuclear power plant, which you kind of turn on and then leave on for a very long period of time, thinking about this at steady state, kind of makes sense. It takes some amount of time for the system to get to steady state, just like your car. It took your car some amount of time to get to that cabin temperature in the wintertime, right? Or I guess now that it's summer, right, you do the same thing with your air conditioner, right, which is removing heat from your vehicle, even though heat is coming into the cabin by heat transfer, right? You can get to a point where the cabin temperature stays the same, even though there's energy coming in and energy going out. Right, so how do we solve a problem like this? Right, so there's one equation and there's 3 unknowns. Right, so we want some equations for m dot, right? So oftentimes, almost every time in this class, although I think there might be some homework problems where this is not the case, but almost every time we're at steady state. So this dm by dt term is usually going to be 0, but you have to tell me that you know that we're at steady state if you're going to cross that term out. So then how do we find m dot, right? Because problems, even directly measuring mass flow rates is a little bit tricky, right? We don't usually do that. Instead, maybe we try to measure velocities. So I don't know if you've ever seen something like this, but this is the idea of flow through a pipe, right? Now, I would imagine probably most people have not taken fluid mechanics yet, correct? I'm going to assume this is when I miss being in a classroom, because people would at least nod. I think that that's true, that most people haven't taken fluid mechanics. So one of the things that we do in fluids is we think about fluids are tricky because it's kind of this continuously deforming medium, right? So what we think about a fluid as little tiny pieces that we call fluid elements, and this little tiny piece of water that's touching the surface here, we say that that has a special condition called the no-slip boundary condition. So if you are that fluid element that's touching the wall, it means that you stay there forever because you don't move, right? While all your other friend fluid elements are floating by in the center of the stream, if you're touching the wall, you have the same velocity as the wall. And if you're a pipe, the pipes typically are not moving, right? But what happens is, when I was a kid, we played a couple of games. One of them was called Crack the Whip. So this is kind of a skating game that I don't know, maybe you shouldn't play because it's a little bit dangerous. But if you're skating, I guess you could do it running too, right? But you're kind of a bunch of kids in a line holding hands, right? Now the person in the center basically stays still, and the people on the outside are running fast, right? So what happens is the people on the outside, the furthest outside, are almost pulling the people on the inside forward, and they kind of run in a circle, and eventually the tension gets too big and people fall down. That's why maybe this isn't the best game to play, right? But this is kind of what happens with these fluid elements, is that this fluid element that's touching the wall has no velocity. It's still because the wall is still, right? But this fluid element here, it's being pushed by some pressure. So it wants to move forward, but it's like holding hands with the 2 elements that are beside it, right? So the one element that's closer to the wall is kind of creating some friction so that fluid element doesn't move. But the fluid element on the other side of the wall, or closer to the center of the pipe here, is pulling it forward. So it's kind of, it gets some, we call it shear, right? Because it's kind of being pulled, right? So you get this velocity profile where you get a velocity maximum here in the center, right? And this kind of parabolic shape is typical of what we call laminar flow. Laminar flow is the case where if you open up your tap, your faucet, maybe in the kitchen or the bathroom, you just open it up a little bit. It's this very clear, sort of beautiful flow. You can look through it, right? But if you really, really increase the flow a lot, then what happens is this flow in the middle, it's going too fast, and the whip, it cracks. So what happens in that case, you get turbulence, and what happens is the fast parts sort of spin out towards the edge, and you get sort of a much more uniform velocity profile. So here, this is kind of a picture of flow through a pipe, right? So we have a bunch of different variables, velocity in the pipe as a function of the radius. We have a coordinate system that's r. We have big R, which is the actual radius, and there's some cross-sectional area here, right? We're trying to get to a point where we can calculate the mass flow rate here. So there's a bunch of terms here. I'm not going to read them all to you. Some that are important here is the density, right? The cross-sectional area, the radial position, the radius of the pipe, and we're trying to find the mass flow rate here, right? So here we'd have to do some calculus if we were going to try to do this. Don't worry, you're never going to have to derive this equation in this class, although you may have to in fluid mechanics. But what you would do is you would integrate from r equals 0 all the way out to r, right? So here you integrate to find the mass flow rate. That's going to be the density multiplied by the velocity times the area. And if we multiplied this out, right, area is in meters squared, velocity is in meters per second, right? So this would be meters cubed per second. So just the velocity times this infinitesimal piece of area. This is like a volumetric flow rate, right? That tells you how many cubic meters of water are flowing through your system per second. But we want a mass flow rate, so we have to multiply that by kilograms per meters cubed. And then we get how many kilograms are flowing through your system in a particular amount of time, right? So now we can change this small element of area into 2 pi r times some small element of radius. This is just showing that the units work out, which I just talked us through. Basically, this is always a good idea when you have an equation, right? We're supposed to be a little bit skeptical when we're learning things. And here, I can't prove to you that this equation is correct, although it's in the textbook, but it does give us the right units. And if it gives us the right units, we at least can't prove that it's incorrect, right? And that's something good, right? So here, if velocity was not a function of the radius, right? In real life, especially in a laminar flow here, velocity is a function of the radius. But what if we take some average velocity, right? And if we think that the density of the fluid doesn't change with the radius, this is a little more reasonable because, density is a function of temperature, but the temperature is probably pretty uniform at any particular cross-section inside our flow, right? So if the density and the velocity are constant, I can pull those out of my integral, right? Or here, if I went my 2 pi rdr, right? 2 pi is also constant. I can pull this out, and now I'm integrating from 0 to r, right? So basically what this tells me is that the mass flow rate is the density times the average velocity times the area, right? Or if I want the density times the average velocity, if this is a pipe, then the area is pi r squared, right? So that's what this particular equation tells me, right? So now I have an equation, but it's sort of pinned on the assumption that the density and the velocity are not changing with the radius, right? In thermodynamics, we wouldn't write it out this way usually, because instead of talking about density, we'll be talking about specific volume, or little v, right? So when we talk about mass flow rates, oftentimes the way that we'll write this out is that the velocity times the area divided by the specific volume is equal to the mass flow rate, right? And in this case, for the pipe, the area is pi r squared, but that won't always be the case. You could have a rectangular duct, and this equation would work just as well, at least the equation in red, right? So now I think anytime we use an assumption, we should always go back to this idea of like, well, does that assumption make sense? Like, is it reasonable for me to do that? Or did I just, The answer, I tell this to my my PhD students and my master's students. At the end you have to do a thesis, right? And your thesis is, it's a chance for you to share the work that you've done, the contributions to science that you've made, and you know, there's always questions about, well, why did you do this way, or was it reasonable for you to do this? And the answer should never be things like, oh, because my supervisor told me to, or oh, I did that because it was the easiest way for me to do it, because those aren't really the questions that people are asking. The question that people are asking, the question we should always make when we're making assumptions is, was this a reasonable thing to do? Right? Every time we make an assumption, we take one step further away from reality. Right? So we have to kind of have, first we have to track these assumptions so that if we want to go back and make our models better, then we know where we made assumptions and which assumptions we can try to tweak. Right? But it's also important to say, like, maybe when I make these assumptions, it's good in one case, but not so good in some other case, right? So it's important to know these things. I think here, the idea that the velocity is approximately constant, or that we can use an average velocity to characterize the flow through a pipe, in most cases is pretty good, right? So we talked about this idea of laminar flow. Laminar flow happens when flows are relatively slow, right? Like if you just open your tap a little bit. But a lot of very practical flows that we'll talk about in mechanical engineering, right? So things like, often flow through pipes, right? But also, if you talk about flow of air over a wing, right? So these are turbulent flows. Now, when you start to do fluid mechanics, you might get pretty attached to laminar flows. The nice thing about laminar flows is that we know what the equations are, and we can often solve the equations to get an answer for what this velocity profile looks like, right? Now, the problem in the thermofluid sciences, right? So this idea of, thermodynamics, heat transfer, fluid mechanics, we know the governing equations. We have a really good sense of what the governing equations look like. But usually we end up at a point where we have too many unknowns for the equations that we have. So most interesting problems in fluid mechanics you can't actually solve with pen and paper, right? So you kind of have to make these models and make assumptions, see if you can drop some terms, look at what's important, right? But, in terms of this particular problem, this assumption ends up being pretty reasonable because it's a turbulent flow. And in a turbulent flow, what happens is, because you get this kind of spinning out, you get these vortices inside the flow, then the velocity profile tends to be distributed more evenly. And even though we might not like the math of doing that, practically it's really good, because what it does is it tends to mix the flow, because here you're showing the average profile, but really it's very chaotic. There's all kinds of, eddies and vortices that are forming, right? In a way that we don't really always understand and can't exactly predict. There's some randomness involved in turbulent flow. We talked about how, maybe in the future, as you're going through courses, if you pick a class that says like nonlinear something, that's kind of like saying it's like the hard version of this. Like nonlinear controls is how do you control systems that are kind of a pain to control, right? Another sort of tip off for this class is going to be hard is if people use the word stochastic. People use the word stochastic because if you say the word random, it doesn't sound very scientific, right? So turbulence, there's some randomness that's associated with turbulence, right? Just like, so if people who model the stock market too, like there's some randomness in the motion of, say, like the S&P 500, which is like a weighted average of the top 500 US companies, right? There's some randomness involved with that, but it's hard to go invest a bunch of money if someone says like, yeah, well, it's kind of a random process, right? So instead we use this fancy word called stochastic, right? Because, maybe you give some money to somebody, if they were looking at turbulent flow and they said, well, this is a stochastic flow, right? So we know the average properties here, but we don't know instantaneously what's going to happen all the time, right? Just like, modeling the stock market, right? Where you kind of know over long periods, the S&P 500 has returned something like 7.5% per year, right? But some years, like this year, you get some wild swings in there too, right? So when we talk about conservation of mass, right? So now I get back to the topic, right? It's reasonable to make these kinds of assumptions because most of the practical things that you'll deal with as a mechanical engineer, provided you're not at very slow flows, dealing with fluids that are very viscous, or if you have channels that are very small, in all those cases, then maybe you'll get to laminar flows. But most practical engineering flows are turbulent, right? So this equation for m dot is pretty reasonable if that's the case. So then these m dot terms, which are different than the dm by dt terms, can be replaced by average velocity divided by specific volume multiplied by cross-sectional area, right? So in that case, our conservation of mass equation becomes this: the rate of change at which the mass is entering or is being stored or removed from the system is equal to the mass flow rate in, but written this way, minus the mass flow rate out. So we can find the mass flow rate if we're not given it. And this is, so oftentimes if you're trying to measure mass flow rate, maybe you'll have some sort of device in here, maybe something like a turbine flow meter that turns the rotation of some fan blades that you stick in there into a velocity measurement. And then you'll know the cross-sectional area of your pipe, and maybe you'll measure the temperature and the pressure, and from that you can find the specific volume. So with those pieces of information, then you can figure out what the mass flow rate is. Or, depending on what you're doing, you can put a bucket at the end of your pipe, and you can measure the change in the volume of water that accumulates in your bucket, and then find the density of your water, right? Or if it's air, you put a balloon on there, I guess, right? So we also have this very special condition, steady state, which means that no mass is stored in the system. So for every bit of mass that comes in, there's another bit of mass that goes out, right? So it's kind of this one in, one out type condition. And that means that our mass flow rate in is equal to our mass flow rate out. So that's what I have for you today. If there are any questions, so again, we won't touch on this in the midterm on Tuesday. So I know that it's sometimes hard to concentrate a little bit, but this is kind of foundational stuff. So it's a good idea to get some understanding of it. I think it's also on the homework for this weekend. So it's a good idea to have some understanding of how to do this. And then also, you can go back and watch these videos in the future as well. So does anybody have any questions about this lecture or about the midterm? All right. If not, then you're free to go. Thanks. Have a great weekend, everybody. Oh, what is the specific time frame for the exam? This is a good question. I think I haven't put an announcement of this on my courses yet, but it is in these videos. So this is from 3 p.m. To 7 p.m. Eastern Standard Time. My time conversions are not great, but I believe if you're in California, that's from noon to 4 p.m. And if you're somewhere in between, then it will be somewhere in between. So right after class, I'll put an announcement up on the My Courses page too. Any other questions? All right. Thank you very much, everyone. Have a good weekend.